my last video, I created a 1000 by 1000 word search, and it's safe to say I couldn't find a single word. But luckily I'm a software engineer and can make a computer do it for me. But I'm not just going to solve it one way, I'm going to solve it in 4 ways. That's right, in this video I'll be using 4 different algorithms to solve tiny 10 by 10 word searches, all the way up to gigantic 10,000 by 10,000 word searches, and hopefully not blowing up my PC along the way. Let's look at algorithm 1. Algorithm 1 is a linear search. Given a word, we will loop through each letter in the grid, starting at the top and moving from left to right, top to bottom. If the letter matches the starting letter of our word, we will traverse the grid in each direction and check if we find the word. Once we find the word, we will repeat this entire process for all the words that need to be found. Algorithm 2 is an extension of algorithm 1 by using a prefix tree. For those unfamiliar with the prefix tree, it is a data structure for efficiently storing strings. A tree is comprised of nodes, starting with a root node. From the root, we insert words by adding a node for each character, and then marking nodes that signal the end of the word. Words that share prefixes share the same path in the tree, making it space efficient. Thus, for this algorithm, we store all the words defined in a prefix tree. We then once again loop through the grid left to right, top to bottom. For each letter, we check if it is a starting letter in our tree. If it is not, we can move on to the next letter. If it is, we check each direction and compare that letter to the next node in the tree. We continue to do this until the current letter doesn't match the next node, in which case we move on to the next direction, or onto the next letter if we've checked all the directions. When we reach a letter that matches a node that marks the end of a word, we can record that we found that word, remove it from the tree, and continue our search. As you may have gathered, using a tree allows us to find all the words by looping through the entire grid once only, rather than needing to loop through the grid once per word like in algorithm 1. Algorithm 3 is a basic random search, where given a word, we pick a random position in the grid. If that letter matches the starting letter of our word, we search in all 8 directions from that position. We continue to pick a random position until we have checked all possible positions or until the word has been found. We then repeat this entire process for each word to find. Algorithm 4 is the prefix tree extension of algorithm 3. We store all the words in a tree and then pick random positions. If that letter matches the starting letter of a word in our tree, we search in all 8 directions. We continue to do this until all the positions have been searched or until all the words have been found. Once again, using a tree allows us to search each position in the grid once, rather than once per word. Once the algorithms had been implemented, it was time for the fun part, testing my creations. To test each algorithm, I created 4 word searches using a random word list from ChatGPT and the generator I made in my last video. Wordsearch 1 is a 10 by 10 grid with 5 words to find. Wordsearch 2 is a 100 by 100 grid with 10 words to find. Wordsearch 3 is a 1000 by 1000 grid with 20 words to find. And Wordsearch 4 is a whopping 10,000 by 10,000 grid with 50 words to find. Now, to keep things fair, each algorithm will solve each word search 3 times, and the average runtime of those 3 attempts will be computed to get a final result. With that in mind, I'll be back once testing has completed. Okay, testing is now done, and we can look at the results. Starting with the 10 by 10 word search. As expected, all the algorithms were super quick due to such a small word search size, but the linear algorithm took the win with an average of 0.089 milliseconds, whilst the random algorithm came in last, taking 0.33 milliseconds. Similar results could be seen with the 100 by 100 word search. Once again, all the algorithms were very quick, but the random algorithm came in last again, taking 67.39 milliseconds. However, this time, the linear tree algorithm came out on top, taking 7.8 milliseconds. Things got a bit more interesting heading into the 1000 by 1000 word search. The random algorithm came in a definitive last place, taking 15.36 seconds, which was nowhere near the random tree algorithm in second to last place, which took 2.09 seconds on average. The other 2 algorithms were within a second of each other, but the linear tree algorithm takes the win, solving the word search in 0.97 seconds. Now for the most interesting and most important results, the 10,000 by 10,000 word search. In last place, taking a huge 1 hour, 37 minutes and 39.61 seconds was the random algorithm. Then we had the linear algorithm with 8 minutes and 41.19 seconds. In second was the random tree algorithm with 6 minutes and 46.22 seconds. And finally, the linear tree algorithm, taking out the win, completing the word search in a tidy 3 minutes and 6.43 seconds, which is 96.81% or around 31.55 times quicker than the random algorithm in last place. We can see that the random algorithm came in last every time, which is unsurprising as randomly accessing an array is generally slower than sequential access. Also unsurprisingly was that when dealing with large amounts of data, such as in the 10,000 by 10,000 word search, the two algorithms that use a prefix tree came out on top. In fact, using a prefix tree in the linear algorithm saw it solve the word search 64.23% faster, and using a prefix tree in the random algorithm saw it solve the word search 93.06% faster. A final thing to note is that in the large word searches, some of the words could accidentally appear in multiple places, due to the word search filling gaps with random letters during generation. Therefore, while the linear algorithms always found the words in the same place, since they follow the same sequential path, the random algorithms may find them in different locations each time, depending on what position it picks first. All in all, this was a super fun experiment and shows the importance of good algorithms and data structures when dealing with large amounts of data. If you want to see the source code and full results, which includes other measurements like the standard deviation and variance, then check out my GitHub, linked in the description. Otherwise, if you enjoyed this video, feel free to check out another one of my videos. Goodbye and see you next time.